So the last convergence test we're going to talk about, the alternating series test, most commonly written as AST. There's one other test called the root test, but anything you can do with the root test, you can probably do with the ratio test. So that one is not particularly useful on a very particular type of question. But in this video, we're going to talk about the alternating series test. And what the alternating series test says is that if you have some series, or you have, and if in the series every other term is alternating, and we denote this by using -1 to the power of n, and when n is an even number, we know that this term will be positive, and when n is an odd number, we know that this term will be negative. And we can count from n equals 1 to infinity. And what the alternating series test says, like all the other tests, an has to be positive, right? If an is not positive, then the fact that it's alternating doesn't actually help you, because we don't know what's going on with an. But what the alternating series test states is that if you fulfill all of these, or the condition that if the limit as n goes to infinity of an is equal to 0, and an and the terms of an are eventually strictly decreasing, so if they're eventually strictly decreasing, then we can say that the series converges. So what do I mean by eventually strictly decreasing? Eventually means that the first few terms don't necessarily have to be decreasing, but eventually, so at some point, so past some threshold point, your sequence needs to be strictly decreasing. And strictly decreasing means that for every an always less than the previous term. And that's basically what eventually strictly decreasing means. So for example, let's go back to our well-known and well-loved harmonic series, except this time let's have 1 over n factorial in front of it. So we can rewrite this as -1 to the power of n times 1 over n, which this portion is our harmonic series, or we can write it as sigma n equals 1 infinity of -1 the power of n over n. And in this particular series, we have it is of this format: an is greater than 0 for values of n from 1 to infinity, as the limit of n goes to 0, an does equal to 0, and an is actually strictly decreasing. It's not even in particular eventually. An is strictly, because 1/2 is less than 1, and then 1/3 is less than 1/2, and so on. So in this example, this portion is our an, and this portion is our alternating portion. And because this series satisfies all of these conditions, we can say that it's converging. So the thing about alternating series is not only do you have to check if the series itself is converging, we also have to check if the absolute value of the series is converging. So imagine it now, we have the absolute value of this, and if we have the absolute value, then we produce the harmonic series. And we know that this series is diverging, as it is the harmonic series. And if we can say that the series itself is the absolute value of the series is diverging, then we say that the series does not absolutely converge, but it converges. And to differentiate between whether we are absolutely converging or converging an alternate theories, we actually call this conditionally converging. And that is the gist of the alternating series test. One thing that should be noted is that if AN is not strictly decreasing, or if these conditions are not fulfilled, we cannot make a conclusion about our theories. We simply cannot conclude from the AST that our theories is converging. We still don't know if